Welcome to the unit on the binomial expansion, combinations and the binomial expansion. The objectives for this session are to use combinations and factorial notation and use the binomial expansion to expand brackets. It is possible to expand expressions such as x plus 2y all raised to the power 3 using Pascal's triangle. Pascal's triangle is formed by adding adjacent pairs of numbers to find the numbers on the next row. Let's illustrate this. We begin with 1 and the rest of the triangle follows. And so on. These are the first 7 rows of Pascal's triangle. The n plus 1th row gives coefficients in the expansion of a plus b all raised to the power n. This does beg the question, is there a more efficient method of finding these coefficients? Because at the moment, each row seems to depend on the previous one. Let's see if we can find a way of finding these coefficients directly without relying on the previous rows of Pascal's triangle. We're going to try expanding a plus b to the power 4 and see if we can spot any patterns. The expansion of a plus b raised to the power 4 is given in the 5th row of Pascal's triangle as shown on your screen. Let's see how we got each of these coefficients. So for the first one, 1a to the power 4, we multiplied all the a's together to obtain a to the power 4. And clearly there is only one way of doing that. What about 4a cubed b? How do we obtain 4? We could either do AAAB or AABA or ABAA or BAAA as shown. So there are 4 ways of obtaining a cubed b. How else could we have obtained this? Let's have a look at the expression on the left-hand side of the screen. Notice that there are 4 times 3 times 2 times 1 way of arranging 4 different objects. However, in our expression, we have that there are 3 a's and 1 b. So any arrangement of 3 a's is going to be exactly the same. So we need to divide 4 times 3 times 2 times 1 by 3 times 2 times 1, as that's the number of ways of filling 3 spaces, times 1, since there is 1b, and that's the number of ways of filling 1 space. Another way of expressing this is 4 factorial over 3 factorial times 1 factorial, or 4 choose 3. And this, of course, equals 4. What about 6a squared b squared? How many ways are there of obtaining a squared b squared? We can either have AABB or ABAB or ABBA or BBAA or BAAB or BABB BA. So there are 6 ways of obtaining A squared B squared, or 6 ways of arranging AA, B and B. Now let's have a look at the expression on the left-hand side of the screen again. How could we have obtained this directly, rather than expanding these brackets? The number of ways of arranging 4 different objects is 4 times 3 times 2 times 1. But we have 2 A's and 2 B's that we're arranging. And of course, the number of ways of filling 2 spaces is 2 times 1. And number of ways of filling 2 spaces here is 2 times 1 also, because we're considering 2 A's and 2 B's. So we have that 4 times 3 times 2 times 1 all over 2 times 1 times 2 times 1 is the number of ways of obtaining A squared B squared. We can write this as 4 factorial over 2 factorial times 2 factorial, or 4 choose 2. And this of course gives us 6. Let's now consider 4ab cubed. How do we obtain the 4? Or how many different ways are there of obtaining ab cubed? We can either do bbba or bbab or babb or abbb. So there are 4 ways of obtaining ab cubed. Alternatively, let's see how we can obtain this directly. The number of ways of arranging 4 different objects is 4 times 3 times 2 times 1. However, there is 1 A and 3 B's. The number of ways of filling 1 space is just 1. And the number of ways of filling 3 spaces is 3 times 2 times 1. And this is why we've divided 4 times 3 times 2 times 1 by 1 times 3 times 2 times 1. We can write this as 4 factorial over 1 factorial times 3 factorial, or 4 choose 1. This of course gives us 4. Now let's have a look at what happens more generally. You'll recall that in Pascal's triangle, the n plus 1th row gives the coefficients in the expansion of a plus b to the power n. Let's see what happens in factorial notation. The number of ways of choosing r items from a group of n items is n choose r, which is equal to, in brackets, n at the top and r at the bottom, which equals n factorial all over r factorial times n minus r factorial, where n factorial equals n times n minus 1 times all the way down to times 3 times 2 times 1. And as a convention, 0 factorial is equal to 1. This is also extremely useful in calculations, otherwise they become problematic. You'll see this later on. We also know that one row depends on the previous row, and we also know that the rth entry in the nth row of Pascal's triangle is given by n minus 1 choose r minus 1. Let's take a look at an example. Calculate 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Which is of course equal to 24. And another example, calculate 4 choose 2. Plugging in the values n equals 4 and r equals 2 in the formula, we obtain 4 factorial over 2 factorial times 4 minus 2 factorial, as shown. This gives us 4 times 3 times 2 times 1 on the top, and 2 factorial times 2 factorial on the bottom. And of course, this gives us the expression shown towards the bottom of your screen. And this tidied up gives us 6. So 4 choose 2 is equal to 6. And this is equivalent to us taking n equals 5 and r equals 3. This is in the 5th row here, and it's the 3rd entry. So 6a squared b squared. Now find the 4th entry in the 9th row of Pascal's triangle. Remember that if we're considering the rth entry in the nth row, then we're looking at n minus 1 choose r minus 1. So in our example, it's 9 minus 1 choose 4 minus 1. And this is, of course, 8 choose 3. And plugging in the values in our formula gives us 8 factorial over 3 factorial times 8 minus 3 factorial, which is 8 factorial over 3 factorial times 5 factorial. And we can tidy up once we've done that. First, we can expand if we're not confident with this as shown. And then we can cancel. To give us 56. This gives the term 56a cubed b to the power 8 in the expansion of a plus b all raised to the power 8. Let's now build on what we've learnt. We're going to have a look at the binomial theorem. The binomial expansion is a rule that helps expand brackets. It gives us an expansion for a plus b all raised to the power n for a natural number n. This expansion is shown on your screen. In the expansion of a plus b raised to the power 4, let's see how this fits in with the binomial theorem. So to find the b squared term, you can choose multiples of b from 2 different brackets. This can be done in 4 choose 2 ways, as shown. And this is, of course, equal to 6 ways. Therefore, the b squared term is 6a squared b squared. We will now apply the binomial theorem to an example. Use the binomial theorem to find the expansion of 2 minus 3x all raised to the power 4. Let's plug in the various values. Here's a equals 2 and b equals minus 3x. N equals 4 and r equals 1, 2, and 3 as shown. Then tidying up gives us 16 minus 96x plus 216x squared minus 216x cubed plus 81 times x to the power 4. Let's now take a look at another example. Find the first 4 terms in the binomial expansion of 1 plus x all raised to the power 9. Again, we have to apply this to the binomial theorem. We plug in a equals 1 and b equals x, n equals 9, and the various values of r. We're really interested in the first 4 terms of the binomial expansion, so we're only going to be looking at r equals 1, 2, and 3. So tidying up gives us 1 plus 9x plus 36x squared plus 84x cubed, and so on. Now let's have a look at another example. Find the first 4 terms in the binomial expansion of 8 minus 0.5x, all raised to the power 7. Again, let's substitute the various values into the formula for the binomial expansion. A equals 8, b equals 0.5 times x, n equals 7, and r goes from 1 all the way up to 6 inclusive. However, as we're only interested in the first 4 terms, we're going to look at r equals 1, 2, and 3. So tidying up gives us as shown. This brings us to the end of this session. If you have understood its contents, you should be able to use combinations and factorial notation, and use the binomial expansion to expand brackets. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.